Hi, everyone, and welcome to this week's Tech Tuesday. As we wait for everyone to jump on here, I'll give a brief introduction. I'm Abby Weber, and I'll be your host today. I work on the marketing team here at FCT Solder, and for today's webinar, we are excited to be featuring Tony Lentz, Field Application Engineer, to discuss automotive solder alloys and electronic reliability. Today's webinar will be recorded and will be available to you through a link that you will get in your email tomorrow. We would love to hear from you during today's presentation, and there will be time for a Q&A session towards the end. You'll see a Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question during today's webinar, we will be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in. Tony, you have the floor.
Thank you, Abby, for the introduction, and thanks everyone for taking the time to join us today for this webinar. Like Abby mentioned, this is about automotive electronics and the reliability of solder joints in those electronics. First, I'll briefly cover automotive electronics and the kind of demands that we place upon them. In other words, what type of environmental conditions they're expected to hold up to. Then we'll talk about the different requirements for solder joints that are in the cabin of a car versus under the hood electronics. And those demands, as you can imagine, are quite different. Then I'll go into some detail on some high reliability solder alloys, including SN100CV and LFC2, which are alloys that Nihon Superior invented. And we'll compare and contrast data for those alloys with other well-known alloys like Inalot. Then we'll talk a little bit about how solder paste and the solder alloy have to have a synergistic effect in order to make reliable solder joints and reliable electronics. And then at the end, we'll have time for questions. So here's a picture of a popular car brand that I'm sure everyone's familiar with. The electronics that are in that car under the hood include engine control units, braking electronics, steering electronics, and exterior lighting controls. The direction that seems to be taken for solder alloys in those applications include high operating temperature alloys that are creep resistant. So they need to be able to hold up to high operating temperatures and pretty wide thermal cycle ranges. And then for power semiconductor die attach technology, silver sinter type products are being used. That environment includes increased operating temperatures, and of course, we have extended warranty periods for cars, many of which last 10 years. That means there's a high likelihood of solder joint failure. So if you need to guarantee an electronic device lasts for 10 years and you've got pretty rigorous environment, that's difficult for solder joints to handle, especially with traditional lead-free alloys like SAC 305. So in that particular application, we recommend LFC2 solder alloy. Now inside of the cabin, obviously there are a lot of electronics being added in the cabin, more and more every year it seems like. So there's obviously instrumentation panels, power distribution electronics, seat electronics, lighting, and audio or infotainment systems all have electronic solder joints. The solder alloy direction for those applications seems to be more towards lower cost and higher yield alloys. And what I mean by high yield is high yield in the surface mount process so that the alloys are easy to work with, some of which have lower reflow temperatures than SAC 305. And they generally are also form reliable solder joints that'll hold up to the conditions in the cabin. And then in some cases, low temperature alloys are being used for the non-safety critical applications. So the increasing complexity of those electronics and cost pressures are really driving folks to try to reevaluate the materials that are used in those types of electronic products. For those applications, we recommend our SN100CV solder alloy. So here's a brief overview of the different types of environmental conditions that these solder joints are going to undergo. So in the cabin, the temperature range in a cabin of a car might be -25 to 60 C, depending on where you live, where the car is parked, how hot it gets in the summer and how cold in the winter. But under the hood, spread that range out to -25 all the way up to maybe 140 C under the hood. Now, actually, I've heard of other vehicle manufacturers starting to require alloys to withstand temperatures up to 180 C for certain applications, which is going to make solder joint reliability even more challenging. Humidity, of course, is going to range. It depends on the environment in which the vehicles are used. Vibration in the cabin obviously is less aggressive, or there's less vibration occurring to those electronics than under the hood. Under the hood, obviously, you got an engine running, it's vibrating. Then as you're traveling down the road, there's road vibration, you add to that. And then if you were to stop suddenly, or in the worst case, get into an accident, of course, that's a pretty aggressive shock that could happen. So shock is possible with all those types of electronics. So these are pretty rigorous conditions for solder joints to hold up to. So the question is, how do we create solder joints that can handle these conditions? So let's talk about the high reliability automotive alloys that are available in the marketplace. These are alloys that were submitted to an INEMI high reliability solder project, and I've highlighted 3 rows in this table. The first row is SN100CV alloy, which is composed of tin, bismuth, copper, and nickel. Then there's SAC 305 highlighted for comparison as the baseline alloy, and that has 3% silver and 0.5% copper, as you all are aware. And then there's Inalot alloy for comparison, which has silver, bismuth, copper, nickel, and antimony. So that's a fairly complex alloy, but it does hold up to under the hood applications for automotive electronics. And that's sort of become the industry standard for under the hood applications. Now, the one thing I want to point out is, of all these alloys that are on this table, SN100CV is the only one that does not contain silver. And I make that distinction because silver has risen in price quite a bit this year. And because of that, the cost of all the silver containing solder alloys has gone up. So that's driving up costs on solder products. Whereas S100CV does not have silver in it, and therefore it's not being affected by the silver market, which keeps costs low for those lower cost applications in the cabin of the automobile, like I mentioned on the previous slides. So high reliability solders operate based on all the elements that are added to them. Here's a cross-sectional picture of Inalot. Inalot is comprised up of a tin matrix with antimony and bismuth that are dissolved in solid solution. It also has Ag3SN intermetallic particles that kind of look like whiskers or dendrites within the solder matrix. And then it has CuNi6SN5 intermetallics as well, which also are solid particles in that solution. So what effect does silver have on thermal cycling of these alloys, or how does a silver help with reliability? Here's a chart of characteristic life on the y-axis with different temperature ranges of thermal cycling on the x-axis. And as you go from left to right, the temperature ranges become more severe, more difficult. So we're going from 0 to 100 C at the left side of this graph to -40 to +125 C at the right side of the graph, and with some temperature ranges in between. So the characteristic life of tin lead is shown there in the blue diamonds. And you can see that that life is stable regardless of thermal cycle. SN100C alloy decreases in characteristic life as you go from less aggressive to more aggressive thermal cycle tests. The same is true of SAC 0307, which pretty closely mimics SN100C. Then you've got SAC 105, which follows the same trend. SAC 205, 305, and SAC 405 all follow the same trend. One thing you'll note, though, is that as you increase silver content with a temperature range of 0 to 100 C for thermal cycling, the characteristic life is much higher. So as you go from 0 silver up to 4% silver, the characteristic life is longer with that less aggressive thermal cycle test. But as you go to the more aggressive thermal cycle test of -40 to +125 C, which has become fairly standard in our industry, there's a convergence of characteristic life. So the life is the same for all these alloys under those thermal cycling conditions. So as the temperature range increases, the effect of silver on reliability decreases. So that means that we need alternatives to silver. We need some other elements or additives to these solder alloys in order to withstand those more aggressive thermal cycle tests. So solid solution strengthening is one way to address this problem. What I mean by that is the element that you're adding to the tin matrix stays dissolved under the conditions in which it's used. It doesn't form precipitates or separate intermetallics. So in this case, what I've got is a chart of new hardness with varying bismuth content increasing from left to right. So as bismuth content goes up, new hardness goes up, and theoretically reliability goes up. So that's one particular element that might help with increasing reliability. But if you add bismuth to a tin matrix, there is a solubility limit. So when you exceed the solubility limit, bismuth will precipitate out as little particles like what's shown here, the kind of lighter gray crystals on the left side of this diagram. You can see that's pure bismuth. And then on the right side of the diagram, you've got Ag3Sn particles and Cu6SN5 particles with bismuth precipitated around them. So particles tend to create seed sites for other particles to grow. That's what's happening with bismuth when it's exceeding the solubility limit of it within the tin matrix. The problem with that is when you have intermetallic compounds as your strengtheners in the solder, they tend to coarsen over time and they lose effectiveness, which we saw in the diagram with silver as a IMC particle strengthener. Silver lost effectiveness as we went to a more aggressive thermal cycle. Intermetallic compounds also consolidate at the interface of the solder joint and the board pad and the solder joint and the component lead. And then those areas where they're consolidating can become brittle spots. And if enough intermetallic congregates in one area, that can become a crack pathway. And so the solder joint could potentially crack through those areas. High strength in solder does not always mean high reliability. So what I mean by that is if the solder joint is too strong, then that can cause pad cratering type defects. Whereas things during thermal cycling, the materials within the circuit board and the solder joint and the component are all different, and they have different coefficients of thermal expansion. And so as those materials are expanding and shrinking with heating and cooling, they're doing that at different rates. And then if the solder joint is not compliant or it doesn't move very well, then it can potentially rip the pad off of the circuit board. So that can cause reliability issues. So solder manufacturers are all coming up with formulations to try to get the best combination of strength, compliance, and stability. So what about automotive alloys for in-cabin use? Here's a chart of tensile strength for SAC305 and SN100CV alloy. And these alloys were tested initially, which are the blue bars, and then they were tested after aging, 500 hours at 150C. And you can see SAC305 lost a lot of tensile strength with that thermal aging, whereas SN100CV was fairly stable with that thermal aging. And that's the difference between particle strengthening, which is what SAC305 uses. SAC305 has Ag3Sn intermetallic compounds that precipitate out as particles within the solder matrix. They coarsen over time and they lose tensile strength. Whereas SN100CV has copper, nickel, and bismuth that largely stay dissolved in solid solution, and those effects of strengthening are stable. So it does not lose tensile strength with this type of an aging test. Here's a chart of creep with SN100CV versus SAC305. SAC305 is the red bar and SN100CV is the green bar. And this is strain on the y-axis versus time in hours on the x. You can see creep accelerates, or the rate of the strain increases pretty dramatically over time for SAC305 because the Ag3Sn particles are coarsening during that, which accelerates the creep. Whereas SN100CV shows a fairly stable creep over the same duration of test. What about shear strength after thermal cycling? So here's a chart of maximum shear force on the y-axis with different types and sizes of components on the x-axis. Again, we have SAC305 in the red bars and SN100CV are the blue bars. And this is data as soldered. So you can see SN100CV has slightly higher shear force than SAC 305, but they both increase as you go to larger size components. After thermal cycling, 2000 hours, -40 to +125C, the shear force drops dramatically for both alloys, but the SN100CV maintains still a higher shear force than SAC 305, which drops off a little more dramatically. Here's some data on isothermal shear fatigue. So this is isothermal fatigue on a copper substrate. This chart is characteristic life on the y-axis versus aging time at 125C in hours on the x-axis. The first line is for SN100C, the precursor to SN100CV. And that has a very stable characteristic life over the duration of the test, but it's a very low characteristic life. SN100CV is the red squares, and that has a much higher characteristic life than SN100C, and it is also stable over the duration of this test. SAC 305 starts out initially with the highest characteristic life, but it drops dramatically and becomes fairly low throughout the duration of that test. So the initial advantage of SAC 305 is quickly lost due to the coarsening of those Ag3SN particles, whereas SN100CV maintains a very stable, clear advantage of characteristic life over SAC 305 in this test. Here's a chart showing different alloys that were tested in a paper by Francis Matuku. This is thermal cycle reliability of some alternative alloys. And you've got tin lead as a control, and then SAC 105 as a control, and then also SAC 305 in the middle of that table as a control. And then those are being compared to SN100CV, Violet, Inalot, and Indaloy 271. Violet's a lower process temperature alloy that is being tested by NASA and the Department of Defense in a lead-free solder project. Now there's two highlighted columns. The first one is precipitate strengthening, and that's the concentration of elements in the alloy that will form precipitates, like Ag3SN, Cu6, SN5, those sorts of precipitates. And those will coarsen over time, and those will lose effectiveness over time. And to the right, there's a column labeled solid solution strengthening. So that's the concentration of elements that will remain dissolved in the tin matrix largely and be more stable over time and not lose effectiveness. This is the test board that was used for that testing, and I've highlighted two of the components, the LGA 97s in the upper right, and then the LGA/BGA 208s in the center. And that's a small selection of the data that I'm going to show you from this work. Here's a chart of characteristic life for the LGA 97 for all those various alloys. And this is for the LGA 97 at a -40 to +125 temperature range. We've got two surface finishes that were tested, OSP, which are the blue bars. And you can see that characteristic life increases as you go from left to right on the chart. For tin lead and SAC 105, it's the lowest, and SAC 305 is relatively low. SN100CV, Violet, Inalot, and Indaloy 271 are all much higher in terms of characteristic life on OSP. That same trend is generally followed on the ENIG surface, although the lives are a little bit shorter on ENIG. Here's that same data for the LGA 208 component for just three of these alloys. SAC 305 in this case is the lowest characteristic life. Inalot was in the middle for that component, and then SN100CV actually has a higher characteristic life for that component on OSP. And then when we ran that test on ENIG, you've got SAC 305 again with the lowest characteristic life, and then Inalot and SN100CV matched each other in terms of life on ENIG. Here's the same data for the BGA 208 component. Inalot had the shortest characteristic life in this case. SAC 305 was a little higher, and that matched SN100CV on OSP. And then on ENIG, that same trend was generally followed, although SN100CV is slightly longer life than SAC 305. Here's data for the LGA 256 with a different temperature range from 0 to 100 C. So this is data as soldered. And what you've got in the red squares are SAC 305, the blue circles are SN100CV, and the green diamonds are Indoloy 271, which had the longest life. SAC 305 had the shortest life as soldered. So this was aged 6 weeks at 125 C, and the same test was run with the 0 to 100 C thermal cycle range. SAC 305 is still the lowest overall life, but SN100CV and Indoloy 271 now match each other on this particular component after aging. That's because the Indoloy 271 lost some characteristic life because of the particle coarsening effect that's occurring in that alloy. Here's a BGA 360 on an ENIG surface. As soldered, SAC 305 has a shorter life than SN100CV. After aging 6 weeks at 125 C, SAC 305 still has a shorter life than SN100CV, although both lost some characteristic life from aging. So what about under hood applications? Here's some data on automotive alloys for that application. This is a performance metric on the y-axis, and then number of thermal cycles on the x, and the thermal cycle range is -40 to 125 C with 30-minute dwells. The blue circles at the top are for LFC2, which is a newer automotive alloy. And then SN100CV is the green circles, which has a lower percentage, especially as you go through the duration of this test. And then SAC 305, of course, you can see drops in terms of performance quite a bit during the 2000 cycles. So SN100CV and LFC2, of course, have more stable performance than SAC 305. Here's cross sections of those solder joints after the 2000 cycles were completed. SAC 305, you can see, has some cracking along the base of the component and from the top of the solder joint coming down. And if that cracking continued, of course, that solder joint would fail and the component would potentially lift off and become a full open. SN100CV is in the middle, and you can see that there's some cracking there as well, but it's not as dramatic as for the SAC 305. And then for the LFC2, that actually has the least cracking shown on the right. You got a little bit of cracking between the component body and the board pad, but not much coming down from the top. Here's data and information on a drop shock test that was performed on those three alloys. So the solder pastes that were used had SAC 305 at the top, and then SN100CV in the center, and LFC2 at the bottom of that list. The component that was used was a BGA 196, and this was done with an acceleration of 1500 grams. And you can see the diagram of the BGA on the left and the circuit pattern that was used. The corners are labeled C1, C2, C3, and C4 for reference. Here's drop shock results for those three alloys in that test. So the SAC 305 are the blue circles on the left, and that had the shortest life. And then SN100CV was the middle performing alloy, and LFC2 was the highest performing alloy, which is the green diamonds on the right. Here are the numbers of tests for the results. So you can see SAC 305, which is otherwise known as SN97C. It's got 99 drops to failure average. SN100CV had 146 drops to failure average, and then LFC2 had 184 drops to failure average. And you can look at the detection disconnection points at the bottom in that table, and those points are all at the corners of those BGAs, which makes sense. That's where the stress is the highest, and that's where those solder joints are going to fail first. So here's some cross sections of those failures. So LFC2 is shown at the top. The crack in that case is running through the bulk of the solder. And then below that, you see a cross section of SAC 305, which has a crack through the intermetallic compound there. You can see the intermetallic cracked pretty completely. Here's a table showing the properties of these alloys. I'm not going to read through all the data in this table. This is in here for reference, but I will highlight a couple of the items on this table. SAC 305 was tested with a melting range of 218 to 219. Typically, it's listed as 217 to 220. The composition, as you know, is tin with 3% silver, 0.5% copper. And the relative cost of these alloys is shown in reference to SAC 305 on this table. So we're considering SAC 305 as the base with 100% cost. SM100CV has a melting range of 221 to 225, so it's a little higher melting range than SAC 305, but it can reflow in a very similar profile to SAC 305. It contains tin, bismuth, copper, and nickel, and the cost of SM100CV is lower than that of SAC 305 because it does not contain silver, so it's about 70% that of SAC 305. And then LFC2 has a lower melting range, 205 to 213. So that I can actually reflow in a profile with roughly 5 to 10 degree lower peak temperature. And so that is advantageous for anyone who wants to run a lower peak temperature or has sensitive components that maybe can't handle a SAC 305 profile. LFC2 does contain silver, bismuth, and copper, and therefore the cost of that alloy is about 30% higher than that of SAC 305. So what about solder paste? And what influence can solder paste have on the reliability of electronics? As a solder paste application engineer, solder alloy application engineer, of course, I'm going to answer yes, solder paste makes a big difference. So here's some information on the types of things that you might want to look for in a solder paste if you want it to give you high reliability electronics. First of all, it would be important to have the solder paste be able to print in a wide area ratio range. This is data from an older paper that we wrote on a no-clean solder paste using SAC 305 type 3 and type 4 and type 5 powders. And the area ratio range shown here is 0.30 all the way to 0.80. And so we're pushing solder paste well beyond the normal IPC standard of 0.66 area ratio. And I just make that comment because as things become smaller and we cram more functionality into a circuit board, and especially more electronics into our cars, space is a concern. Obviously, auto manufacturers want to utilize all the possible space under the hood of the car and in the cabin, and they want to use microelectronics to do it. And so that means printing solder paste through smaller apertures. And so it would be important to pick a solder paste that can print through really low aperture area ratios. The other thing we'd want a solder paste to do is to be able to reflow in a wide range of profiles. We know some automotive electronics are fairly thermally demanding when it comes to the surface mount process. And it's important to be sure the solder paste can handle maybe a long soak or a higher peak temp or a longer time of liquidus and still give you a quality solder joint without building a thickener metallic layer. And then there's other cases where maybe the automotive technology is not very complex in terms of the circuit board, and you want to run that in a really short, fast profile in order to mass produce a lot of electronics really quick, which is more what I've seen with our automotive customers. But you want to make sure the solder paste can hold up to both of those profiles and still form a proper solder joint. Small deposit coalescence is becoming more important as we go to more smaller solder joints, microscopic components. With this particular diagram, this is a griping test that we like to run. And so when I say small deposit coalescence, I want to make sure that that solder powder reflows completely and forms a smooth contiguous solder joint and not have individual solder powder particles that are sitting there like a bunch of grapes that could potentially have a weakness in it and crack and fail. Pin testability seems to be becoming more important. I know a lot of our clients do pin tests through the flux residue. So it would potentially be important to have pin testable flux residues that are good for longer than 5 days. And then of course, we also know that a lot through-hole components are becoming less common, but there are still cases where surface mount technology is being soldered along with maybe 1 or 2 connectors that are through-hole. And so it's advantageous to have a solder paste that can be printed for those through-hole components and reflowed at the same time as the surface mount components without dripping out of the hole, and giving you a proper solder joint and proper barrel fill. So pin and paste capability is important for solder pastes as well. Now, I'm talking specifically here about one of our solder pastes. And in this case, we tested it for printing over an 8-hour time period with print and pauses. And so what you're looking at is a chart of transfer efficiency initially on the left at time 0. And then after 1 hour, 2 hours, 4 hours, and 8 hours on the printer. And you can see the transfer efficiency data is fairly stable over 8 hours on the printer with long pauses. And that's important because we do have customers who are maybe run a first article where they'll print 2 or 3 boards, fully assemble those boards, then put them through testing. And it might be 2 or 3 hours before they start running the line again. And so it's nice to have a solder paste that can hold up to that and then just print immediately without any issues of printing on that first board. We also test all of our solder pastes for reflow performance, and 3 categories that we rate them in are wetting, solder balling, and graping. And in this case, I'm comparing AMP1 PT, one of our newer no-clean lead-free solder pastes, versus a comparative paste. And you can see it has higher ratings on wetting, solder balling, and graping, or improved performance in all 3 of those categories in terms of reflow. And then, of course, voiding is also a concern. And so AMP1 PT is one of our AMP1 series of solder pastes, which are ultra-low voiding solder pastes. And so on this particular QFN component, the void area is less than 1.5%, which is important for anyone who has issues with voiding. And I'm hearing more and more limits being applied to voiding of 25%, sometimes 15% for really critical devices. And that's challenging. If you're having a voiding problem, I mean, there's lots of different ways you could approach that problem, but switching solder paste is one of the things you can change in order to reduce voiding in your solder joints. Head and pillow is also a concern, and it's important to have a paste that can handle head and pillow or potentially prevent that. And the ways that we would address that problem is making sure you have enough activity in the solder paste to hold up to, say, longer soak profiles and still have enough flux activity in order to remove the oxide from the solder powder and from the BGA sphere, and then give you a proper solder joint. But also what's important is solder paste that has a rheology that allows it to stretch, so it can maintain contact with the board pad and the BGA sphere if the BGA warps during reflow, which is fairly common for larger BGAs. And so that warpage can create a separation and create this problem all by itself. So if you have a paste that'll stretch, and like I said, with the proper type of rheology, it can minimize the potential for this problem. And then also important, of course, for no clean solder paste is the flux residue and what's in that flux residue. How reliable is that? And so in this case, AMP1 PT is a 0 halogen, no clean flux. It passes IPC, JIS, and Telecordia SIR and ECM tests. And of course, there are lots of different varieties of SIR and ECM, but these are 3 of our common industry tests that are pretty aggressive and pretty rigorous. And we want to make sure the flux passes all of those tests. So here's a summary of what I've talked about. There are lots of high reliability solder pastes that are available. There are different elements that are used to enhance the strength of the solder alloy. And those include silver, bismuth, indium, copper, nickel, and antimony. And in some cases, those elements can affect the cost of the alloy, especially things like silver and bismuth. Solid solution strengthening that's used in SM100CV and LFC2 gives a more stable effect than particle strengthening, which is used in SAC alloys, which tends to degrade over time. And so we recommend SM100CV for in-cabin electronics and LFC2 for under-the-hood electronics. And certainly automotive electronics are being built every day, and they have the lifespan that's required in order to fulfill the warranties that are guaranteed by the auto manufacturers. But that has to be achieved through the correct use of alloys and the correct solder paste for the application. So it's important to pair the demands and the requirements of the solder paste and the alloy with the application, of course. Thank you all for your time. We really appreciate it. And now we have time for questions.
Thanks, Tony. Yeah, I've seen a couple questions come in here. The first one is, Can BISN AG 2% solder be used for applications for automotive application under the hood?
I wouldn't recommend that, mainly because under the hood, we've been told that temperatures can exceed 140 C, or like I mentioned earlier, in some cases, 180 C is a new requirement for at least one manufacturer. And so I'd be concerned that that bismuth tin alloy would melt and then you'd lose contact with all of your solder joints.
Sounds good. Thank you. And has SN100CV or LFC2 been approved at any automotive companies?
They're both being used in automotive applications, and they're both undergoing approval testing with different companies because different companies have different requirements. I don't know the specifics. I'm not really in touch with their sales department, but somebody could get back to you with specifics if you're interested in that.
Great. Has FCT done reliability studies on BISN AG compositions?
We have not done any ourselves on those compositions. I know there are papers available from past technical trade shows that have some studies on bismuth, tin, and silver mixtures. But I'm sorry, we have not done that ourselves.
Sounds good.
And we also are happy to answer any questions after this webinar is complete. My contact information is on the presentation. So please get in touch if you have anything as a follow-up after we're done here.
Yep, definitely. Well, if there are no other questions, oh, here's one. Is the characteristic life data for different temps based on Weibull data?
Yes, that was all extracted from Weibull data. I just didn't want to show all the data. If you actually look through those two studies, there's extensive data, way too much for like a 30-minute webinar. But we'd be happy to share those studies if you're interested in all the data.
Thank you. What is upper limit on silver addition to improve reliability?
That is a good question. We haven't specifically studied the upper limit. My understanding from other work that I've read is 4% seems to be around the upper limit where highest reliability was achieved, and adding additional silver above 4% didn't give much more benefit in terms of reliability. And then of course, there's also cost to consider when you're using the high silver contents. So I think 4% is roughly where that sweet spot is between reliability and cost.
Thank you. What is impact of, in addition to improving reliability?
Of indium?
Oh, of indium, sorry.
Yeah, we have not studied indium specifically, so I can't really comment on that. I know that is used in some of those high reliability alloys. So I'm not sure. I believe it has a similar effect to bismuth, where it lowers the melting point, but it also integrates into the intermetallic structures in a certain way.
Mm-hmm.
So I'm sorry, I don't have a lot of firsthand knowledge with indium.
No problem. We appreciate your insight. Well, as we are coming up on our time here, we'll start wrapping things up. So thank you again, Tony, for joining us today.
It's my pleasure.
And thank you everyone for your attendance and participation. Just as a reminder, this webinar was recorded and you can access it through a link you'll receive in your email. As we mentioned before, don't hesitate to reach out to us with any questions. Oh, yes, so you'll get a copy of this presentation through a link in your email tomorrow. Be on the lookout for future topics, and we look forward to seeing you in August for the next Tech Tuesday. So have a great rest of your day, everybody.
Yeah, thank you, everyone.
Thanks, Tony. Bye-bye.